Alright, so this is the first video covering the content in Math 1560 Calculus 1 for the fall semester at the University of Lethbridge. In this video we're going to introduce the concept of a limit. We're not really going to do much with it, we're just going to kind of discuss some of the general ideas. So before we get into limits, let's talk a little bit about generally kind of what's the idea with calculus. So everything that we do in calculus involves the real numbers. You can talk about calculus over the complex numbers, but that's a subject for another course. We're working with real numbers, and so the picture that you've probably seen for the real numbers system is you've got this number line, right, and zeros in the middle somewhere, and things go off to infinity in one direction, and they go off to minus infinity in the other direction. And we know there are infinitely many real numbers, but in some sense, there's not infinitely many real numbers in the sense that there are infinitely many integers. They go on forever. But there are infinitely many real numbers also in the sense that even if you take a tiny, tiny, tiny piece of this number line, somewhere like this, you cut a piece and you zoom in. No matter how far you zoom in, the real number continuum looks like the real number continuum. There's no level of zoom where you start seeing things separate out and you see spaces between the numbers, anything like that. It is continuous, and this continuity is one of the things that allows us to do calculus. And in a course like this, we unfortunately can't really get into those details. That's something that you'll see in a more advanced course like Math 3500, but it is kind of something that's going on in the background, right? When we talk about limits, we always talk about being able to make values as close as we want. There's this idea of arbitrary precision that comes in when you're working with the real numbers. Now, everything that we kind of deal with is going to involve functions, right? So the usual kind of idea, function is some sort of creature that takes an input, right? X here is my input, and it produces some sort of output. We often call that y, especially if we're in the context of graphing. And most of the time, if we're in this calculus context, the sorts of functions that we deal with are ones given by formulas. So maybe, I don't know, maybe this is something like, let's say the top half of the unit circle, right? So we can talk about functions like that. We could graph this if we felt so inclined. We could draw a graph. It would look something like that, and we could use the graph to understand the function. But we're interested in studying the behavior of functions. We're interested in studying things like, is a function well behaved? Is it continuous, like this example here, where the entire graph is one nice unbroken line? Does the graph go up? Does it go down? If it does, how fast does it go up? How fast does it go down? And one of the reasons that we care about these things, of course, is that functions are used to model a lot of physical phenomena, right? When we'll be talking about, increasing, decreasing functions, we'll be talking about slope and curvature and things like this. We'll kind of look at things from a geometric point of view, but if you're coming at this from, say, physics, you might be talking about velocity and acceleration, or if you're coming from, say, an economics point of view, you might be looking at, rates and changes in markets, or I don't know, whatever it is economists do. And all these things that we're going to study in calculus fall under this banner of limits. So we're going to begin with this idea of a limit because from limits we get to many other things. Limits are going to give us derivatives. They're going to give us integrals. They're going to allow us to make approximations. Almost everything that we do in calculus can be phrased in terms of a limit. And limits are basically, these objects that allow you to kind of think about approximations and figure out, well, when can you take an approximation and make it precise? Can you turn an approximation into an exact answer? That is pretty much the game that you play when you're doing calculus. All right. So just to give you kind of a rough idea of the sorts of things that we consider when we're talking about the idea of a limit. Limits ask this question, you're given a function, so you know how to produce its output values if you're given the input values. So if somebody hands you x, you know how to get y, and so what you're really trying to do is you're trying to say, okay, can I take those y values, can I take those outputs, and can I make them get close to a certain value, right? And how do I adjust the y value? Well, the y value depends on the x value. So what we're really asking is, can I choose the input appropriately to get a desired output? And so the limit lets you kind of think about this in terms of, well, maybe I can't put in the exact input that I need, but maybe I can put in values that are close to the input I really want, and I can look at what happens there. So if we were looking at a graph like you see here, we could talk about limits for something like this. And so we might be able to talk about limits at a point like, let's say when x equals 4. I don't know if I can tell you exactly what that looks like. It's about 1 there, right? So when x equals 4, I can kind of think about what the y value is. And that looks like it's about 1. So I might be able to say things like, well, I could say things like this: f of 4 equals 1, right? The function value at that point is equal to 1. But also I could say that, if I considered values of x that are just a little bit to either side, if I considered an x value here or an x value there, right, then my points on the graph are here and there, and my y values are not too far off from the true value, right? And as I squeeze those points in, these two little green points, if I squeeze them in towards 4, the closer they get to 4, the closer the y value is going to get to 1. And this is the general idea of a limit. Of course, you can see there are some other points on the graph where this is never going to work. If I was interested in the value of a limit at, let's say, 2, right? Well, then I run into a problem, because if I consider x values that are a little bit on this side of 2, I'm hitting the graph here. If I consider x values that are on this side of 2, well, then I'm hitting the graph way up there, right? And you can see that it doesn't matter how I play around with those, no matter how close I move these in towards -2, I'm never going to be able to bring these y values together. There's always going to be a gap between them, and so I can't say that I can make the y values as close to a certain value as I want by adjusting the x values, because we have this gap, right? Or if I look at what's going on over here at 3, it looks to me like there's a bit of a vertical asymptote going on there, like this graph is heading off towards infinity if I were able to fit the whole thing in. And so then that presents a whole other sort of problem that you might have to deal with. So we can think about limits graphically. We can also think about limits numerically. We could think about a function like this: f of x equals e to the 2x minus 1, all divided by x, right? And we're interested in the values of this function. We're interested in the sort of outputs that we can get from a given input. And you say, okay, what can I get out of this? Well, can I talk about things like what's the graph look like near 0, right? Well, I certainly can't talk about f of 0. What do I get if I tried to put that in? Well, maybe I'll put equals in quotes here, because we're going to get nonsense out. What do I get? E to the 2 times 0 minus 1 over 0. Well, we all know that you can't divide by 0, so we're definitely running into trouble here. But notice also that, well, 2 times 0 is 0, so this is just e to the 0. Anything to the power of 0 equals 1. So I've got 1 minus 1 up top. This simplifies to 0, 0 over 0. So I'm dividing nothing by nothing. It doesn't make any sense, right? It's a completely nonsensical statement to talk about 0 divided by 0. So this doesn't work. But maybe I can talk about, well, what happens if I'm maybe not putting x equal to 0, but what if I consider really small numbers, so values of x that are close to 0? Well, then you get something like this table here. Okay, instead of trying to plug in 0, I can say, well, okay, let's try 1, right? I mean, in the sense of if you're working with integers, 1 is pretty close to 0, but if you're working over the real numbers, 1's still pretty far away. I get this value of f of x. So I move in a little closer. I go to a half, I go to a tenth, I go to 1 over 100, 1 over 1,000, right? 1 over 10,000. I move in closer and closer, and we can see that as I keep moving in, it really looks like these y values are getting close to 2. And so we might be tempted to say that the limiting value as x approaches 0 here, the limiting value for this function would be 2. And that would be correct, and we will look at some methods later in the course that might let us deal with that. Actually, for this particular example, we might not quite touch on some methods that would work. You might have to wait for Calculus 2 to tackle that guy. Okay, so before we end this video, let's just make one remark that if we come back to the beginning, the stage that everything takes place on here is the real number line. But what about real numbers themselves? We kind of understand the integers, we understand the rational numbers. Once we get to irrational numbers, though, these are really hard to understand. And most irrational numbers are things that we don't have nice expressions for. Think about something like pi. Okay? Well, we know we can write down this decimal expansion for pi, right? There's people that compete to see how many of these digits they can memorize. You can use computers to generate as many of the digits as you want. But they never end. There's no end to the digits in pi. There's no pattern. There's really nothing that you can do. There's no way that you can kind of write down a rule that tells me what all those digits are. They go on forever. They don't have a pattern. They don't repeat. And so how can I describe that number? How can I describe it numerically to you? The best I can do is give you an approximation. I can choose some point where I stop writing down decimals. I'm not giving you the true value of pi. I'm only giving you an approximate value for pi, but I can give you a value that is as close as we want to the real value, if I include enough decimal places. This also kind of fits in this limiting idea that if you go far enough, if you do something, if you get close enough, if you kind of do things often enough, you can make an approximation as good as you want. Here's another one. This number e, the base of the natural exponential function. Here's an approximation for e. It doesn't work very well if you put in n equals 2, 3, 4. It's not great. But if you play around with this, if you keep plugging in larger and larger values of n, go up to like 50, go to 100, try plugging things in, you will find that this expression does actually output values that are pretty close to the true value for e. And you can show that in the limit, if you take n large enough, if you kind of let n become arbitrarily large, you can make this value as close to the true value of e as you want. So even numbers sometimes end up being expressed as limits. All right, so that's it for the introduction. In the next video, we're going to look at how to manipulate limits. We're going to look at some of the algebraic properties that they satisfy.